today's material may be second or third hard in the whole course. There will be new philosophical concepts that we need to absorb in complement to equations or instead of equations or together with equations. And the basic idea for today will be how to go from many electrons to one electron. From our discussions in previous meetings, you probably remember and aware that it is the biggest challenge, that a large number of electrons in a molecule is very hard computationally. And since you are already practicing Hartree-Fock method, you see that there are molecular orbitals that are filled by one electron or maybe two electrons, right? On one hand. On another hand, we all know that wave function, that molecule consists of many electrons. So how can we set up an equation for molecular orbital? How can we take signatures of electron-electron interaction in many electron wave function and many electron Schrödinger equation into specific equation for one electron object, for one electron orbital. So while I'm setting up the screen, you may, if you have custom to take notes, please try to write by your own word this thought, and maybe you will do it better than I can do. So we need to import signatures of electron-electron interaction into one electron problem. So try to write it down, and I'll go sharing the screen. What to expect today? I plan to arrive to one figure in the middle of the lecture and a set of equations at the very end of equations, hopefully. So the figure here, I know it is ugly, and maybe I'll ask you in new homework to do something better, or we will just agree that it can be drawn better. So in the last lab, you did learn how to plot molecular orbitals, right? And we did look at least on two orbitals, HOMO and LUMO, for titanium hydroxide, right? And you probably have noticed that these orbitals show localization on different parts of the molecule. Like HOMO is localized on oxygens, and LUMO is localized on titanium, right? Do you remember this? We'll focus on it once again in the coming lab, but here is the feature that orbitals do not coincide with each other in space. They occupy different areas of space. Why? Can anyone tell why these balloons take different areas of space? Like if you take different orbitals, they are localized differently. Lina, do you have?
So as we said, each electron has a specific state. So each orbital should have a particular space.
Mm-hmm. Okay.
But not, I don't think they are overlapping or something.
Okay, yeah, so it is point number one, that in a good quantum system, orbitals form orthogonal set that obey orthogonality, and therefore they shouldn't overlap, right? So yes, but this is correct even for one electron object. But there is you are correct, but there is another mechanism. Boston, would you like to give another point of view why orbitals are typically placed on different parts of molecules?
Besides that's where they're energetically favorable. I couldn't give you more detailed answer than that.
Can you just read first line of the slide? I know it's my ugly handwriting, but can you just read it and comment?
Like the electron-electron interaction, or the potential between electrons is the sum of the 1 over the separation distances.
Yes, thank you. So since orbitals, occupied orbitals are occupied by electrons, it means electrons sitting on one orbital and another one repel each other. And if they would appear in exactly the same areas of space, the interaction energy will make such configuration very unfavorable. So due to electron-electron interaction, they have additional mechanism to make them distant, far away from each other. And this is main idea of today's meeting. If I will be lucky to come to the end of the lecture, there will be a slide full of equations, this one. And because I'm not sure if everyone is able to stay until the end, let me comment on these two equations, which are the most important thing. The rest will be just explaining where they came from. So we will consider, and do not look on the ugly handwriting yet. Now it's better. So we will consider simplest multi-electron wave function, basically composed of 2 electrons. And we will try to formulate an equation that will work for first electron. So, and then instead of Hamiltonian, we will have something more complicated that will be like Hamiltonian for electron 1. And then for electron number 2, we will have another equation, you see here, phi2. And I use Dirac notation because it is a little shorter. And then it will be, instead of general Hamiltonian, it will be something specific for electron number 2. So the goal of today's meeting is to get agreement with an idea generally that it is allowed to go from multi-electron wave function to one electron equations. And second, how to formulate this particular Hamiltonian that acts only on one electron. So if this equation looks too long and incomprehensive, do not worry, do not panic, because it is a result of long derivation. Just in case, if you plan to leave literally in time and I will not be able to finish. So this particular Hamiltonian for electron 1 includes kinetic energy for first electron, then repulsion of the first electron with all nuclei available in this, not repulsion, attraction of the first electron with all nuclei, and then there will be very, very specific object that shows how the electron number 1 is affected by electron number 2. So it is the word that Lola was asking. So in some sense, it is signature of multi-electron interaction into one electron equation. Like in this, okay, I need to go forward with materials to show at least something. But if you have general question about the idea, please feel free to stop me and ask. Okay. So our now very brief overview what we did in previous lectures. So we all agreed with about Slater determining shape. Our plan is to get Hartree-Fock equations, and right now we are at the stage of learning mean field. So this word that I called signature, the good word for it is mean field, because all but one electrons create an average mean electrostatic field that affects our preferred electron. Slater, quantum numbers for single electrons, the Dirac notation in spin, and later on we were playing with orbitals. So so suppose we take a molecule, nail down positions of ions, and then do a crazy thing. We ionize it. We remove all electrons so that we have only ionic skeleton. Then we bring back only one electron and let it take the shape that it wants to take. Make sense? So the electron that we place back to this ion will be attracted to positively charged ions. So it will localize around ions, as I showed here with this red line. If I try to return back another electron, it will not be able to sit on the areas of space where the first electron was, because it will be not only attracted by ion, but also repelled by electron number 1. Therefore, the second electron will take a shape that will focus on other areas in space, which do not coincide with the first one. Are you okay with this idea? Here, I give some comments that Hartree-Fock theory is actually a theory how to go over this major challenge, how to include electron-electron interaction in one electron equations. And if we are able to more or less adequately create equations for one electron and find orbitals, then these orbitals can be used as building blocks to compose overall multi-electron wave function. So the orbitals that you have seen on the last lab, they are not quantum states of the whole molecule. They're only orbitals. And to describe the whole molecule, one needs all occupied orbitals. So one needs to bring them together. So please give me a little sign if you are comfortable or discomfortable with this first line equation. And Boston, you can either you can use if your camera doesn't work, you can use the additional symbols or just say by word. So please show like
Looks all right.
Or you can put camera and express your happiness or not happiness with the first equation. So let me ask help of Lina. Would you please interpret what the first equation means in your, how would you interpret it?
Okay, so the first equation is the potential energy, and it's so here the integration over the different over the distance between the two electrons.
Mm-hmm.
And yeah, it depends on the difference between the two electrons.
Okay, yeah, everything is correct, but maybe we can add a little bit more to complete it.
Okay.
Boston? Would you be willing to add a comment about this equation?
So yeah, like she was saying, it's the integrals over the positions of the electrons, and looks like is that the I'm blanking on the name for it.
So let me give a hint, and then maybe if you tell it, it will be much, you will express it in better, in more elegant way than I can. So there are three concepts behind quantum theory. There are operators, wave functions, right, and matrix elements. So wave functions are vectors or functions. Operators are matrices or things that include two variables, and matrix elements are numbers, the result of convolution. When you were practicing orthogonality, like Brian had, you get a number, like matrix element. So based on this hint, Boston, would you qualify this line? Is it one of the three, or it includes one of this or several of these three?
So I'm blanking on for the wave function with what the star is called.
Conjugated.
There you go. Thank you. The complex conjugate. There we go. So is that the expectation value for the?
Excellent.
That's what I was trying to get to. My brain was shutting off.
Super. Thank you so much. Yes. And can you? I suspect that the word expectation value is not most favorite word in our class yet. So just to make sure that everyone on the same page, can you tell briefly what is expectation value?
So from my understanding of it, it's similar to kind of like the average value. It's not equivalent to it, but it's basically what you would expect to find in your system If you were to take a measurement of it, obviously there's chance involved, but that's like the most likely outcome.
Really great. Thank you. Thank you. And probably you are tired of speaking. Now I'll continue. So the part here, as Lena correctly told, this is Coulomb operator. So it's electron repulsion. I can put it like V, this little head, and tell that it is electron repulsion. Right? Positive sign. Now, phi of R2, and probably we need to have indices, otherwise it will be not literally correct. So this is, so phi 2 of R2 is wave function of the second electron. Phi 1 of R1 is wave function of the first electron, right? Now, if you have a multiplication of the phi 2 star phi 2, if I look on this object, how do I interpret it? What it is? Wave function absolute value squared. Phi star 2 times phi 2 equals phi 2 absolute value squared. So what is the definition of this thing?
Can I answer?
Please.
So the definition of this is the probability to find the particle in a range of space in a. So if we multiply this, the expectation value with the DR2, for example, this would be the probability to find the particle in this distance DR2. And
excellent. Excellent. So Lena did answer it in the absolutely correct way as a person who studied quantum mechanics. No criticism. But in the community of computational chemistry, there is secondary interpretation of quantum mechanics, which is not widely accepted in the overall community. So it is philosophically doubtful, but it is really helpful for practical applications. So one can interpret this product also instead of letter P for probability, one uses letter rho or letter N and calls that it is density. So it is density of electron. So instead of electron being probable to find here and there, one can speak that electron is not a point charge, but it is some flexible object that is spread over the space. So on the right, we have density of electron number 2. On the left, we have density of electron number 1, or probability to find electron 1, right? Now, so I have, let me do a picture for this. So green, yellow, and blue. So green is electron 1. Yellow is electron 2. And blue is their Coulomb interaction. So R1 minus R2, as we accepted in classical physics. So this expression with integrations adds together possible localization of electron 1 and 2 in space and add their interaction energy to the average value. So this expression tells the number what is energy of interaction of electron 1 and electron 2 if they occupy orbital 1 and orbital 2. So the blue, the science stuff in the middle is operator, and the result of integration is expectation value, is the average energy. And this is the thing that makes our life hard, because to practice it, we need wave function for electron 1 and electron 2. And objectively, it's hard to solve equations for more than one wave. So although time is almost finished, but now let me start the lecture. So the equation that I'm going to process will look this way. And on the left side, we have standard electronic Hamiltonian, right? Kinetic energy, nuclear to electronic, and electron repulsion. In here, I will approximate wave function of two electrons, 1 or 2, as a product. So briefly, for today's lecture only, I will, or for even several minutes, I will forget about Slater determinant and just use product. Phi 1 R1, phi 2 R2. Everything what we do can be done in the continuous function notations. But since personally I am lazy and I want to avoid writing the symbol of integral, I will use this angular bracket Dirac notations, because the integral d R1 phi 1 star R1 something here 1 R1. So you see it's quite long expression, and one can simply replace it by the notation phi 1 phi 1. So the Dirac notation is just used as a shorthand. Now, in the previous years, if you will look for the recordings, we were playing in the game of Wheel of Fortune. I was asking to everyone in the class to guess the keyword for this expression when one converts two wave functions and operator into a number. But I think Boston already gave the answer. So Boston, please stay silent for a minute. Let me ask for the rest of the class. So which words can be placed in these yellow boxes to adequately represent the underlined equation? Please try. Or you can, if you do not have the whole word, you can try different letters. Sarah?
Expectation value.
Yeah. Okay. Yeah. Thank you, Kay. This year class is too strong. You know you gave the answer right away. Yes. Expectation value.
Value is
expectation value.
okay. It's E.
And generally, this is definition of expectation value in one electron quantum mechanics. And in today's lecture, we need to do some additional thing, some little bit crazy thing. So what if, just a second, I'll try to formulate. I'm sorry for this 5 seconds delay, but it is really an important step. Remember, we were discussing energy of interaction of electron 1 and electron 2, right? It's we spent noticeable time on this slide, and I was covering the parts of equation. So there we had electron density of electron 1 and density of electron 2 on different sides of Coulomb attraction, and we got a number. So what we were doing there was, let me write it down in the Dirac notation. We were doing phi 1, phi 2 operator V, phi 1, phi 2. And we told that it is expectation value of Coulomb interaction. So on the left and right from the operator, there are two wave functions, and I believe we used different colors: yellow, blue, and green. Do you remember this equation and our discussion? Please just show yes or no. Just show, so Lina remembers. Kia? Yes, Sarah? Lola?
No, I don't remember.
Okay, that's fine, that's fine. I'm going to jump a few slides back, so it is here. So this equation has this yellow electron number 2 and green electron number 1 and Coulomb interaction in the middle. So the part with star is bra. So it is phi 1. Think with star phi 2. And the wave function without star is k. Phi 1, here phi 2. So we have total 4 wave functions and 1 operator. Do you, okay? Well, are you okay with this?
Yeah, thank you.
Okay, good. Now it is here. So we have bra for 1, bra for 2, cat for 1, cat for 2. So two wave functions from the left and right of the operator. This is typical and standard thing. And now so now I'm going to say the most important thing, that it's only the last equation at the bottom of the line, but it is a very strong philosophical concept. And it is not usual, it is not practiced in basic quantum courses. So prepare. We will do partial averaging of the operator. So for complete averaging, we need to have so many brass and so many cats as many independent particles, as many electrons we have. And here we are going to practice less. So instead of 2 brass and 2 cats, we have only 1. So we will average an operator that depends on 2 electrons only over spatial localization of, let's say, second electron. Then this object, and the tilde means that it is partial, it's neither operator nor a number. So in respect to second electron, it will be expectation value, but in respect to electron number 1, it still will be an operator. So its expectation value for electron 2, but it is an operator for electron 1. If you find it complicated, it is very normal. It is very hard concept that I was not able to get for several years. But this concept is the one that Lola did ask at the very beginning of our meeting. This is the signature of electron number 2 that would act on electron 1. So maybe try to write down your own words about this procedure, about this partial average, and I'll ask you to share your writings, your words, maybe later, and let me check if I can really rush through things or I need to postpone things to the next time. So here is the plan. I know that some of you need to depart and I do not want to hold you. So I'm going to quickly skim through the rest of the slides without long discussion. And if you need to disconnect, please do, because you have your plans and your schedule. I'll just do a brief overview of the remaining slides for today's lecture for recordings. And then next time when we meet, I will go over them once again because they are important. But if you are on the schedule, I'm not holding you, please feel free to disconnect. And I'm going to go over a quick demonstration for practicing of this partial average. Okay, so formal meeting is done. Do not worry if you need to disconnect, it's completely legitimate. And now I will start, set, go, like a sportsman. Okay, we multiply left and right part by wave function of 2. Then left and right part will be partial expectation value in respect to electron 2. Then since electronic Hamiltonian has 3 terms, we can apply this partial average to each of them, but keep the electron number 2 away as independent variable object. And here with 1. Electron 1 is independent, so we are doing equation for electron number 1, and this product of phi 2 times phi 2 will be 1, same as you did in the homework. So this object that is hard to give name is so-called reduced operator. So it's reduced means we have performed averaging over the position of electron number 2. Now I briefly go over each term. So reduced operator of kinetic energy applied to operator for electron 1 will be the same as operator for electron number 1. If you apply it to electron number 2, it will be expectation value for electron number 2. Then I practice the partial averaging to nuclear to electron attraction. And then there will be total 4 terms if you have 2 ions and 2 electrons, and 2 of them will become operators, 2 of them will become numbers. And the last term, electron-electron repulsion, it is what is most complicated and most important. So instead of having 2 bras and 2 cats on left and right, you'll have only 1 bra and cat. So we'll average over the position of electron 2, but it still will be operator in respect to electron 1. Then, if you take our overall molecular Schrödinger equation and subtract from expectation value from eigen energy the expectation value of kinetic energy and expectation value of interaction between second electron and nucleus, it will be the energy that there will be remaining energy that will depend only on features of the first electron. And if I plug in all these things into molecular Schrödinger equation, I will obtain an equation that, so here is reduced eigenenergy, and here is reduced operator. And one can do the same procedure both for electron 1 and electron 2. Whew. I understand that it is not understandable in this way, but we'll start next lecture from repeating and discussing. So I know that you need to depart, so done. Now I'm inviting you to disconnect.